Okay, we're about to start. So, good morning, everyone. And our first presenter is Kwaki Han, and he's presenting altimetry-derived shelf-edge currents of western coast of Canada. Okay.
Hey, thank you, Nicole. Yeah, so good morning, everyone. I hope you had a good time last night, for the dinner. And today I'm going to talk about altimetry-derived shear-edge currents of Western Canada. So this is a simple project, but in support of state of Pacific Ocean reporting in fisheries and oceans of Canada. So the project is supported by Canadian Space Agency's Surface Water and Ocean Topography program. So we are looking at the Northeast Pacific, and the North Pacific current flows eastward towards the US and Canada coast in the mid-latitude at the surface, and it separates into two branches. One is the forward-flowing Alaska current, and another is the equatorward-flowing California current. And over the shear edge and continental slope, so the flow is a little bit more complicated in terms of this mean circulation pattern. So in the winter time, the flow is forward flowing, and in the summertime, it's equatorward flowing, because this is kind of a conference or transitional area. Okay. So for this area, there's lots of oceanography observations, but mostly it's temperature salinity. In terms of ocean currents monitoring is really scarce, and especially the long-term ocean current monitoring for climate study purpose. It's almost only one site. There's a kind of 30 years of observation for ocean currents. So really, altimeter can play an important role in monitoring ocean currents for this region, just like any other regions in the world oceans. And here we are looking at the climatological monthly mean wind pattern. So left is for the winter, January, and on the right is July. So you can see off the Canadian coast, the wind in the winter time is predominantly forward, and in the summertime is predominantly equatorial. Okay, so this has a very important implication, or it's a very important driver for circulation pattern changes in this region. So as I mentioned, long-term monitoring of ocean currents are really limited for this region. And so the purpose of this study is to use satellite altimetry to observe long-term variability of ocean currents and hopefully provide some useful information for state of the ocean reporting in support of ecosystem management. So we also want to improve our knowledge on interannual and alongshore variation of the near-surface current. So we use the topics Poseidon, ESA-ESRIN series along-track sea level anomalies for the period from 1992 to 2020 from rates. And we derive geostrophic surface current and normal to satellite ground track. So on the right here, you can see the blue segments are the selected 6 ground tracks. Okay, and as you can see, those ground tracks approximately perpendicular to coastline and the ice bath. So it's a good proxy, for the along shear current. And here you also see this red circle is a long-term monitoring site over the shear break. It's at about 500-meter ice bath. And the square is the location of the meta-ocean buoy that measures surface winds. So first, we did a comparison of the altimetry-derived geostrophic currents with the long-term the in situ measurements at the monitoring site. This is a 35-meter current. So you can see altimetry is below, current meter data is in red. And clearly you can see, the mean current is almost zero, both in the in situ observation and altimeter data. So this means actually the satellite, the mean sea surface from satellite is quite a good representation, even at this kind of scale, okay, small scale. And if you look at signal availability, I think there's a very good agreement between altimeter and current meter data. And in terms of interannual availability, there's also reasonably good agreement. So with the long-term correlation about 0.6 significant at the 99% confidence level. And if you calculated the difference between altimeter and observation versus the observed current from current meter data, you can see the ratio is actually quite small. That means the altimeter has a good skill in observing the alongshore currents. So here you're looking at the detailed circulation at the satellite track on the south end. Okay. And the dashed dotted line is the mean current, and the blue is the seasonal climatology, and the red is the seasonal mean. So positive means forward, okay? So as you can see, again, the mean is almost zero at this transect, very weak, and the seasonal cycle with a range of about 8 centimeters per second. It's forward in winter and equatorward in summer. And you can see some strong episodical anomalies, okay, like this part here, here, and here. And so those episodic anomalies are coincident with El Nino or La Nina events. And this slide shows the altimeter-derived currents at the middle of the study area, okay? And so now you can see the mean current is forward, okay? The dash dotted line, and it's about 80 centimeters per second. So the seasonal cycle, the range is about 12 centimeters per second, and still is winter time is more forward, and summertime is kind of more equatorial. Okay? So we also notice some substantial interannual variation. That's a bit difference between red and the blue. Okay. So now the northernmost transect. And now you can see the mean current is still forward in the northern part, but the seasonal cycle is almost zero, diminishes. And instead you see quite significant interannual variations. Okay? So in terms of this, alongshore changes of circulation pattern, so we can see the seasonal cycle mean or changes from south to the north. And what about the interannual variations? So we have done some EOF analysis for currents at these 3 transects. And this shows the first mode. It accounts for about 45% of the variance. And the lower pattern is the time series of the first mode EOF. So we can see this first mode EOF represents the northward forward current, okay? And you can see that significant interannual variations associated with the first mode EOF. Now we look at alongshore wind anomalies. As I mentioned, in the beginning, and there's a dominant wind pattern change from forward in the winter to equatorward in the summer. So if you look at it, this is the wind anomalies measured at buoy off Vancouver Island, and the lower pattern is the wind anomalies measured off Oregon. Okay, so they have quite coherent patterns, if you between these two sides. And we also calculated the correlation between the first mode EOF, the altimeter derived currents, and these wind anomalies. And we found the altimeter currents are both significantly correlated with the local winds of Vancouver Island and the remote winds of Oregon coast. So in calculating this correlation, we have accounted for autocorrelation between time series. And we also look at the Pacific Decadal Oscillation Index and the NINO 3.4 index. And because that's the popular climate index, people usually try to link to them. And however, when we calculated the correlation between altimeter current anomalies with the PDO and the NINO 3.4, we found there's no significant correlation. So now we can take a look at the results and try to have a brief, summary of the relationship between the altimeter currents, the alongshore wind anomalies, and PDO and El Nino. So we found, the altimeter current anomalies are significantly correlated with alongshore wind anomalies of Vancouver Island and of Oregon state. When we examine the current anomaly patterns, we found some strong anomalies during El Nino year or La Nina years. However, we did not see significant correlation between altimeter-derived currents and PDO, or between altimeter-derived currents and NINO 3.4. So obviously, it's more complicated if you want to link the local current change to large-scale climate index, but clearly it's directly forcing, or related to the local alongshore wind forcing, and this probably not just about tropical process, but involve, local bioclimatic adjustment too. So to summarize, in this simple study, I show the utility of satellite altimetry for long-term monitoring of shear edge flow of Western Canada, and the surface shear edge currents correspond to both regional winds of West Vancouver Island and remote winds of Oregon. So although there are large episodic current anomalies during the El Nino and the La Nina events, but we do not see any significant correlation between the current anomalies and NINO 3.4 or Pacific Decadal Oscillation. So the last slide. So the results I showed previously is only from 1993 to 2020. So as I mentioned, the main purpose here is try to use altimetry data to support the state of the ocean reporting. So we do need this kind of results just with latency of probably about 1 month. We need to report and to be included in the ecosystem, state of the ocean report. So this slide shows the results from 1993 to 2022, and so you can see in the last few years, the currents of West Vancouver Island is mostly more equatorial. This is during the consecutive 3, La Nina years. So we have tried to, as I mentioned, this is for the shear edge current. So we would like to actually derive this kind of simple index to provide information for ecosystem science and fisheries management. But the coastal altimetry products, sometimes there are issues with the delay, and we have looked at like CTOH extract data. Usually the update, they have done tremendous job, but the update, because of the challenge and difficult, is not as the data in the RAISE system. So we hope this can also be available in the future, and so we can provide truly a coastal currents for the state of the ocean report. Thank you very much.
Okay, thank you. Any questions?
Hi, Gertrude. And mostly comments. First of all, I really like this. It's a very relatively small study, but it's so instructive for people who are new to this. This is the perfect thing that you can throw out to students because it mentions climatology, it mentions seasonal changes, it mentions EOFs. You have everything there that is perfect for. So I would like to borrow this at some point so that they can use it when I need to give some instructive presentations or something inside, because this shows exactly how Altimetry can be used for a very simple purpose. About the delays, of course, you're aware that most of the products come out already after 3 hours, so that's far within your 1 to 2 months. That doesn't have the most accurate orbit, but you look at slopes, so that should not matter. Then there are the 3-hour products, the 3-day products for actually 1 to 2 days, 36 hours in case of Sentinel-6, and I think it's 48 hours in case of day 3. And then, of course, we have the 1 month product for Sentinel-6, 2 months for day 3. So you should be able to do this, but then of course, you need to set it up to derive your occurrence. But I think this could be very valuable for Canada to have this, as a regular product that you turn out, so that because the purpose can be passed. It's nice to see. Thank you.
Okay. Yeah. Thanks very much, Renko, for your nice comments and for your information, right? And I think this is a very important, and so I really look forward to it. And for Sentinel 3A and C6, so now we have several years data, right? And it's so, as you said, it's available within a few days, or definitely with good quality, maybe within 1 month. That's great. Yeah. So certainly we will use this, incorporate this into this kind of analysis. Yeah. Okay. Thanks very much.
Okay, any more questions? Okay.
A quick question to Wolfie. Yeah, it's a very interesting study. I'm intrigued by this very clear seasonal signal that you've got in the climatology. What happens when you look at the single months? Are there even stronger currents than 6 or 7 centimeters per second in one single month? Because if I understand it correctly, these are 3-month mean.
That's right. That's a 3 months mean. Yeah. If you look at a single month, yes, would it be much larger? Yeah. And also, so we need to first, if you look at 1 month, would be much larger anomalies, right? And also the magnitude depends on how you calculate the scale of spatial scale you look at. So if you look at the comparison slide, that's different. Those are calculated at about 100 kilometer scale, right? And so if you calculate, in order to compare the altimetry with modeling data, so we cannot calculate like within 100 kilometer segment. So our magnitude will be significantly underestimate. So we have to be very close, to the modeling site. Like here we use 25 kilometers. Because why we choose 25 kilometers in calculate the altimeter current? The first one is this. I think there's a presentation yesterday shows like below 60 kilometer wavelengths, the altimeter signal will be significantly degraded. Almost it is not good, right? So we choose 25 is about half of the wavelengths. And so I think it's still probably altimeter is valid for this kind of scale. And on the other is if you calculate geostrophic current, you cannot choose your scale too small. If you're too small, probably spatial scale too small or time scale too small, the geostrophic variance probably is not that well. Not a good assumption, right? And so there are several considerations in there. So to point of your question, if you look at the monthly, magnitude will be much larger, but the error will be also larger. So when we use the seasonal mean, we calculate the error at 100 kilometer length scale. If it's a seasonal mean, then you are looking at the error about 1.5 centimeter per second. Yeah, but if you use a monthly mean, then your error will increase by square root of 3, I think. Times 1.73. Yeah.
Okay, I think we have to move on to the next presenter now. And we have so this presentation is by Majid Mostavi from Tallinn University of Technology, and he's actually a PhD student of mine. And his presentation is about accurate dynamic topography by satellite altimetry and marine geoid model. And he's a PhD student, has been working on this for about 4 years now.
Morning, everyone. Thanks for the introduction. So today, my pleasure to talk about my latest result for the accurate dynamic topography using the satellite altimetry product. To start, I start with some basic definition. Dynamic topography is the difference between the sea level and the geoid, and which is a more realistic component of sea level variability rather than the sea level anomaly, which is referred to a mean sea level, which is changing during the time, that's not stable. And the dynamic topography DT can be derived by 2 approaches, geodetic approaches, by tide gauges, which is also valid near the shore, and satellite altimetry also by oceanographic approaches using mathematical modeling, hydronic model. So in this figure, I show the methodology part of the study, and as you can see, we can validate the dynamic topography by satellite altimetry along the coast, along the track, using the hydronic model, although the hydronic model datum is mostly undisclosed or unknown. So the assumption is that the model provides the accurate sea level, but not precise, so it can be corrected by a simple shift using the tide gauge data nearby the satellite track, and then the satellite can be validated along its track using this corrected model. So the objective of this study is to develop a method to determine this accurate dynamic topography along the track, and then use this dynamic topography use the model to validate this dynamic topography, and then finally to determine some specific problematic area with persistent or semi-persistent behavior by synergy of this data set. And the tools we have here would be accurate, high-resolution GeoID model, and also Alice plus SAR and Alice plus retracker dataset provided by Baltic Seal, which has shown better performance rather than standard products. So what I want to point out here is that the model can provide high resolution, both spatial and timely, although it's not refer to a realistic kind reference, but it can be corrected by the tide gauge data, which are accurate, and then the satellite can be validated. So the flowchart of the study is shown here. First the data set, then the correction of the model, and then comparison it with the satellite data to get the final map of the Vincent. To start, the data set, we had 47 tide gauge stations along the Baltic Sea, which provided by 9 countries, and these tide gauges have been reconstructed and corrected for the land uplift using the NKG 2016 land uplift model, and the GeoID we used was the NKG 2015. And the hydrologic model we used was the data assimilated hydrologic model by SMHI. Here you can see the error between the model and the tide gauge at the location of the tide gauge during this time period. The seasonality can be also seen from the figure. And the satellite data, as I mentioned, we use along track 20 Hz data of Baltic Seal project data. Almost 4 million data points, and the data have been corrected using this flowchart. And what I want to point out is that we didn't use any quality flag. Instead, we used the careful data screening to remove the bad quality data and outlier selection. And then by having this data set along these tracks, we can compare the data. So here you can see an example of one track, Sentinel-3A, the satellite data, the blue line, and the model data, the corrected model, which is mostly underestimating the sea level comparing to the satellite. And when we do it along the whole track in Baltic Sea during the time period, here's the standard deviation. And as you can see, the north part of the Baltic Sea, the subarctic part, has the highest standard deviation. The black dots are presenting more than 20 centimeters standard deviation, and which is mainly due to the sea ice presentation. Especially for this winter season. What I want to show here is the Sentinel-3B. We had only 8 months of data available. So, and they're like mostly during the winter season, so that's why you can see higher standard deviation there. And by comparing along track RSE, here you can see the pattern of the RSE of each mission. And as you can see, the JSON-3 is more overestimated rather than the Sentinel missions, especially north part of the Baltic. And by normalizing those RNSE, we can find the problematic areas, which could be due to various reasons. Here I mentioned some of them. The purple one are the one who could be mostly the satellite issues, and the yellow one, we doubt that there could be a problem with GeoID, and the green one is mainly due to the tide gauges quality at those areas. And as a summary, I want to mention that the core component of this study was utilizing the high-resolution geoid model to retrieve the accurate instantaneous dynamic topography, and which is where more which is obtainable using the geoid, and it's more preferable rather than the sea level anomaly, which is referred to mean sea surface. And large standard deviation values can be seen over complex part of the Baltic Sea, especially at the coast and subarctic area. And by synergy of different data sets, we can reveal the inconsistency between the data set and also improve them. And by multi-mission comparison, the problematic area can be investigated. And I want to thanks for the data provider, Special Baltic Sea Project, SMHI for the model, and the tide gauges, and the provider. And this research has been granted by Estonian Research Council. Any question? I would wish it. Thank you.
Okay, any questions? Okay, no questions? Okay, so we go to the next presenter. And this is myself, but Saeed Rajabi Kisari is going to do it. He's another PhD student of mine, and his title of his presentation is Forecasting of Absolute Dynamic Topography by Utilizing Machine Learning with a Synergy of Satellite Altimetry Data. And this is a new study that we're just about to start, so it's initial results, basically, for where we're heading. Okay.
Hello everyone, good morning. I want to talk about forecasting of absolute dynamic topography using machine learning and satellite altimetry. At first, having reliable sea level forecasting is necessary for a range of disciplines, mainly the safe navigations, coastal protections, and climate change issues, also the operational forecasting system and planning decisions. Machine learning, with its capability of handling large-scale problems, also the nonlinear relationship, so it can provide us a good forecasting results, and but like the non-linear relationship, like what we have for sea level, actually. And I want to give some initial background on machine learning, because I think this is the only presentation on this topic at this workshop. So machine learning has different components. The first is input data, a set of predictors or observations, and it tries to find the best function or the best hypothesis maps by minimizing the loss function and to have a final forecasting model. There are various machine and deep learning models that have been developed for the sea level forecasting. In the recent years, mainly are the convolutional neural network and also the recurrent space neural networks, like we have, for example, the LSTMs. Actually, there are deep learning models, which is a more complicated version of machine learning. And we have two main challenges for sea level forecasting, and I want to address these two with the solutions. The first is regarding the input data. We have different sources of sea level data: tide gauges, altimeters, hydrodynamic models, and also GNSS. They might have different and similar spatial temporal resolutions, for example, SA and TG. Also, as my colleague explained in the previous presentation, we have the hydrodynamic model which has unknown vertical reference datum. So the Druid can make the link between these data sources, and here the solution is to use a corrected version of the hydrodynamic model that has been validated by a vast network of tide digestion around the Baltic Sea. So I use this DT data, which is linked with the high resolution NKG 2015 Druid to my forecasting model. So the next challenge will be regarding the methodology and implementation. There are two general approaches for sea level forecasting. The first are the autoregressive models, which solely based on the historical values of the observations here in the sea level. And the second approach is the physical models that relate the physical or hydrometeorological features to the final target sea level parameter. The best available autoregressive model has the correlation coefficient of around 90%, and also the physical models work in 1 week ahead with an accuracy of 85%. So our objective and solution is to integrate both of the methodologies by proposing it hybrid modeling to overcome the limitation of applying each of the methods individually, to have a forecast of dynamic topography in a spatial temporal domain, and finally validate the results by satellite altimetry data. The study gap is more regarding the reference datum. Actually, most of the previous study have used the machine learning for related sea level predictions, like what we have, for example, for sea level anomaly and also the extreme values. But the literature is still limited for absolute sea level prediction, for example, the SSH or DT. The study area is the Baltic Sea region, and the data comes from different sources like sea surface temperature, wind components, zonal meridional, surface pressure, and also the DT we used from the corrected HTM model. We also add the temporal day of the year feature, seasonality, and finally we validate results by satellite altimetry aligned for SSH with 20 Hertz frequency from Baltic Sea, Sentinel-3A. As the data comes from different sources, I just forgot to mention that the data were collected for 3 years, 2017 to 2019. And the data comes from different spatial temporal resolutions, so we sampled them to daily means and also gridded them to a 25% degrees. This resulted to 731 grid points for all the Baltic Sea region. In the figure, you can see the scheme for the interpolation technique. The flowchart, the first 80% of the data was used to train the model, and the rest 20% was used to test the model, to check the model performance. And we used multivariate one-day ahead prediction by using a two-dimensional convolutional neural network, which is a deep learning model. And finally, we validated the model by various tracks after applying the corrections and the fencing with Joey. About the proposed model structure, I named it as Conv2D model. First, we have different source of data, so we made a sliding window of the inputs, and then we go to the main layers for the Conv2D, which are the convolutional, pooling, and fully connected layer. The convolution layer performs the convolution operator by multiplying some of initial weights with the input data to extract the general features. The pooling layer is used to shrink the dimensionality of the model, and finally, the fully connected layers feed the vectorized outputs from the flattened layer, as you can see in the figure, and feed it into the feed-forward neural network. We have some initial parameters like the activation function, number of epochs, optimizer, loss function, and also a number of neurons in the dense layer. And the implementation was done by Python 3.9 version and also using the cross and TensorFlow frameworks. And by the equation, we want to find the best function of f to relate the predictors to our final forecastability, especially temporal domain. First, we did some feature engineering between the predictors. As you can see from the top figure, left one, the wind component U and V had great correlation with the with our DT, and also the sea level pressure had a correlation of around 40% with DT for most of the Baltic Sea points. Also, the SST had some correlation around 25% in the middle Baltic here, and also the collinearity analysis was done between the input features to find some highly correlated features and delete them into the modeling. And as you can see, we have 25% correlation between the pressure and zonal wind component. So we kept all of the variables into the model. The implementation results shows that the conv2D model could predict the sea level for training and test set by an R squared of around 95 and 91% respectively. Also, the RMSE was found to be around 4.7 centimeter, which shows the good performance of the applied model. They also plotted a special RMSE plot for the test data for around 6 months for the 2019. And as you can see, for most of the grid points, the errors are within 5 centimeter. Of course, there are some grid points in the southeastern part of the Baltic Sea that we can observe higher discrepancies like 10 to 12, 13 centimeters. Also to evaluate the open loop forecasting of the our proposed model at the special domains, we have selected 4 random grid points, C1 to C4, and as you can see, the red ones are the red nodes are actual data, and the predicted the blue lines are the predicted values. So for all of the points, you can see there is a consistency between the model and the actual data. Also, the red error bars shows the discrepancies of around 4 centimeters for most of the points. Also, there are some months like for July, or I guess also in January, that there are discrepancies of around 10 centimeters. We validated the results, final results, by 4 tracks of ESA-ESRIN, the altimetry data. The figures compares the 20 Hz ESA-ESRIN and the smooth 1 Hz ESA-ESRIN, also highlighted by yellow nodes, which shows the nearest points to the grid node. The red square are the observed HDMDT, and our predicted conv2D dynamic topography is the blue one. As you can see, for the tracks 483, 483, and also 711 311, also 614, which are in the, for the cycle 45. We can see that the trends between our proposed model and forecasted model, also with the original HTM model and the 1 Hz DT are inconsistency, and the discrepancies are mostly around 5 centimeter for all the tracks, except for 311 that for one grid point, which is the coastal grid point, actually, the row is around 20 centimeter. The point I should mention here is that, as you know, the satellite provides instantaneous sea surface height data, and but here we used a daily forecastability, so to study the suitability of comparing our model with the satellite altimetry measurements, we compared different statistics between the model, the original HTM model, our ConfDD model, and also the satellite data for the previous tracks I mentioned. And the statistics are the median, the red line in the box plot, and also the maximum minimum extreme values. And as you can see for track 483, we have more comparable values between the SAE measurements and also our proposed models. This track encompasses the middle to southeastern Baltic Sea. Also for track 311, we have seen that there is a distinct pattern between the data sources, but if we go to the previous slide, we can see that this track has a limited number of grid points. So, but anyway, for the uncontaminated points, which are situated in the upper quartile, there is more consistency between the satellite and model data. Anyway, for tracks 711 and also 614, also having similar median
Okay, 3 more
values.
minutes. 3 more
We can
minutes.
see the smaller box plots when compared the model and the SA measurements. So it suggests us reduced data range and also smooth daily values when compared to the instantaneous satellite observations, which may hint us about the future studies to apply higher spatial temporal resolution. And as summary, we used a multivariate-based convolutional neural network model to forecast dynamic topography in the Baltic Sea. The statistics showed good performance of the proposed model by R-squared over than 90% for both training and tested. The RMSE was found to be 4.7 centimeter. Based on the special RMSE plot, the higher discrepancies were observed in the southeastern Baltic Sea, the RMSE of around 10 centimeter, which can be due to a different source of input data that I use here for SST and wind rather than the HTM simulation. We also validated the result with aligned track SA measurements from Baltic Sea, and the results confirm the agreement between the two data sets by RMSE lower than 5 centimeter. Still, we have observed that for some tracks, for example, 614 and 711, we have a smooth stability when compared to the satellite measurements. So, for the future study, we can use a higher spatial temporal resolution, maybe for addressing the longer time span. For example, 1 week, we use here for 1 day ahead DT field prediction. Also, we can add other features that were not considered here. For example, river discharge or surface salinity. And also this study used the satellite altimetry data for the validation phase of our model, which is high frequency in the spatial domain. But the future study, we plan to have the satellite measurements as the inputs of the model. So if we refer to the proposed flow chart from the step 2, we can combine it with the step 1 to have the SM measurements as the model inputs. Finally, the research was supported by Estonian research councils and we thanks to the data providers. Also, the results of this presentation was submitted to a journal and it's currently under review. And thank you for paying attention. I will come any questions.
Thank you for your nice talk. For the training, did you try to use the stress, the surface stress, the two components of the surface stress?
No, I use the wind components, UMV,
Yeah.
and also pressure and surface temperature. Also the OI. No, this was selected based on the previous study because I wanted to forecast in short term. So the previous study all agreed on these components, these variables. So, but you mean this can be considered for?
Of course, yeah. You can check if you can use in the training.
You mean the geostrophic currents components?
No, it's the surface stress. It's from the wind part, but it's surface. I think it can be used. It can be checked.
I think it can have.
It's more sensitive than the wind at 10 meters, for example.
It can have correlation between this stress and also wind components. So
yes, of course, yeah. But
we should delete one of them
it
into the model and apply it.
should be interesting to see what is the percentage of the impact of such parameter in the training. But it's just a suggestion.
Thank you for comments.
Okay, I'm not sure. Any more questions? Okay, any more questions? Okay, I just make a comment about it to stress that what we actually saw from the satellite data is that it's showing more information than even the models. So the small scale processes, you can actually see it. So this is why we want to actually take the satellite data and bring it into the input so that maybe it can also predict some of these small scale processes. And this may be one of the areas that we are heading to next because the satellite has much more information that we're not using. Okay, so.
Thank you.
Okay, so now for the next presenters, I'm not sure if they're here. Is it K.E. Kemgang Gumsi? Yeah? No? No? Okay, maybe the next presenter then, M. Hernandez Gonzalez. Wow. Somebody party last night. Okay, I'm not sure. Maybe we wait for them or.
Yeah, so we can ask Jerome. Jerome, the last two speakers are not here, so shall we just end this part of the session and have a coffee break earlier? So what's the time now? What's the time?
10. Exactly
10, okay.
So what time is the coffee break? Soon?
It's 10:40, so they are 40 minutes.
Okay, so the coffee might not be set up and ready, so it might not be useful to make a coffee break now. We can show the seed questions. Did you put them on PowerPoint?
No, not yet.
Question for the discussion at the end of the day.
Yeah.
We could put them up so you can infuse them and think about it during the day and talk about it during lunch. Do you have
See the question, not.
seed question on the computer? And meanwhile, we find this, if this is ready or not. We have made a certificate of attendance. So if you want to pick it up at the registration desk, you have a beautiful certificate of attendance.
That's nice.
And yeah, so USB key with here. Alors, pour la libérer, attends. Pas comme ça. Elle est mounted. Ça, et système de la lumière. Et d'accord. Maintenant, tu peux l'enlever. And so, the chairs, do you just want to present them or read them and maybe make some comments? And so there are 2 slides. And we could just go through them just as questions. Eventually, eventually comment on them.
Okay.
Just to get ready for the discussion this afternoon, or even start the discussion now. It's not? Yeah.
I think we will defer this to the discussion period, right? Yeah, so we will wait for all the presentations done, then we'll have some discussion.
Yeah, no, we have a discussion slot at the end of the day, that's sure. But you can anticipate on bringing and asking, for instance, I mean, you can just spend some time silently to read it and think of additional one which we're missing.
So many of the questions that we ask have been already asked during the past meeting or also the past days, but maybe some of you can add other input to answer to the different questions. And we also added a question about how we know that a product that is proposed as an R&D product is mature to be pushed for operational production, and how we ensure this transfer to operations. Then, do you want to comment
which one? Okay. Okay.
So Ben, I really would like to stress the importance of that third bullet point that you got there. So how are we going to enable the production of postal altimetry, the inclusion of postal altimetry to operational products? So I hope there will be a little bit of discussion, perhaps a contribution from our friends who are in charge of the operational chain, so to update us on what is done already, and also there are production and what might be perhaps ideas for the future, like adding one specific product of the postal strip, so on in the operation. I think that's a very important point, and we eventually give a big push to the adoption and use of postal altimetry data. So really bring all the research and development that we've seen in these workshops over the years, we will bring it to full fruition towards the users. So that's a crucial point.
Okay. We also had, I think, another about the synergizing of the data sets. What we found is that there's different methods being used, especially with tile gauge data and satellite, and there should be some kind of conformity, especially if you're looking at different areas to actually compare each other. And we think that the vertical reference datum is an issue that should actually be looked at seriously if you want to compare and to act accurately. If you're going to operational mode, you need to have it down to a good reference datum. And actually the geoid is one of the main components that is often overlooked. And what we want to look at is it really needed? Is it important to you or not, actually? And should we attempt to improve the geoid, the marine geoid, so that there's some consistency amongst the different data sets, among different countries, so it's one conformity that is being used in one method? And what about the uncertainty? If you're actually going to come out with a product, you need to have your uncertainty or errors in your product for somebody to actually use it or to feel reliable to use it. And how is this all calculated? And what we found, at least in our research we're doing in Tech, is that there's lots of information the satellite is actually showing you that is not being used. The small scale variability is not being used. We're just stuck on validation. And this is the point of it. The satellite gives you information at the coast. Yes, this is good for validation. And it also gives you like waves and these processes that can come. But also it's one of the only sources of sea level offshore. The hydrodynamic models gives you a smooth sea level. It doesn't show you the small scale variation, but the satellite is actually showing you this. So the question is, how do we now include this to get to understand what's actually going on in the oceans? And this is what we want to find out. How can we actually use this effectively, this data that is all there? So this was one aspect that we think needs to be addressed. And so something to think about.
I will say that I don't know if there is an answer for that, because for everything satellite, for models, you need the validation to know that when you are analyzing that signal has a physical meaning. So I don't know if there is a way to avoid the validation part. I don't think so. Maybe our effort is like, yes, it's true, not to stuck to try to, if you get a product that you are satisfied, maybe it's not the accuracy of 1 millimeter, but it's the proper accuracy to work with that, maybe to start working, and then start to validate it again, to improving the accuracy, like baby step. I get my product and I'm satisfying enough to analyze the data. Then I can go forward and make it better, and start and again analyze the data. It's a proposal. I don't know if it's the best option, but I don't think that we can avoid validation of the data, because when we're analyzing the physical meaning of these signals, we can make a mistake because we don't have a good validation.
Could you perhaps elaborate some examples of small-scale features in the coast, in the sea level?
I didn't hear you. We didn't hear you.
Could you elaborate the examples of small-scale features in the coastal areas in the sea level perspective?
What we see is a variation. When we compare it to the model, you're seeing more variety in actually the long tracks than if you have a model. So we don't know what it is exactly, but it's worth exploring or including into it. We think that machine learning can help actually to incorporate it, in that it can actually help you identify the scale of these processes, and both temporally and spatially, and that might help you identify these processes. But there's lots of information in the satellite data itself that is there.
Maybe I have a little bit of idea, but coastal altimetry may have all this altimetry is noise in the nearest the land. So if you're interested in sea level, we might be saying just not exactly we, but there might be some effort to put in a pressure sensor along the track of the altimeter and see whether this is small scale feature real or not, because there's not enough observation available in terms of the sea level in cross-shore direction. Along-shore direction might be some of tide gauge available, but I don't see that much along cross-shore direction or along track of that altimetry aligned with that. There's no sea level observation.
The idea is not just to only use satellite altimetry. There's actually ocean color data. There's lots of other satellite data you can actually bring in to make a good picture, to actually see what is there. And this is why there's another method that can actually help with this. And this is, so it can take all the features that are there, or the values that are there in your area that you're looking at, and can come up with connections if there's a relationship with it.
Independent observation, not by satellites, in situ observations.
Yes. Yes, in situ is really important. Yeah. Thank you. I think we had some other questions. Yes, we had some other questions.
Something to this thing. I don't know if it's really related. I don't see. So, when we are looking to a particular coastal region, perhaps there exists data that that were done in campaign or shipped, and we have our altimetry, but they don't use our altimetry, and we don't know that the ship exists.
Yes.
So probably it's necessary to open a little bit or to address to particularly, perhaps there exists also a website where this is written, but we don't know, and we find afterward.
Yes,
so
that's
this is probably, because if we want to validate altimetry, we think, okay, we take the tag gauge because anyway they are always available, but there are surely also ships that regularly do something. I am now realizing some in my region. And without contact with them, I would not think that they can do. Yeah.
Yes, and there's shifts, and everybody's using different shifts.
Sorry?
And everybody's using different shifts, and the shifts in the data just to match it to the tide gauge. Sometimes there are shifts that
but
are biased.
the shifts are used by a sonographer, for example, to
Yes, exactly.
the model, but the people working with altimetry would like also to have a look, but it don't know that it exists.
Yes, exactly.
So probably it's important to get this information. Yeah.
And it's also important to know what corrections were in the tide gauges that you get. Sometimes you don't download tide gauges and you don't know what corrections they've actually implemented in processing the tide gauge data. Have they considered land uplift? How they detided? What they actually done into it? And so this is why it's important to know the data sets and also the uncertainty, and the method used to calculate it. And I think this is when you go to validation and to putting out products out there, you need to consider these aspects too.
Yeah. So perhaps we try to for some region, yeah.
Yeah.
For example, for the Baltic.
Yeah, we've been doing it. Yeah, we've been working on it. So we have some more questions.
I have a question about the validation strategy of sea level, not the sea level trend, but the sea level. I mean, for 30 years, we have been validating altimeter data, basically sea level, significant behavior, and wind speed. In the case of sea level, we have been using for 30 years a specific location of the tide gauge around the world when you try to find one track close to your tide gauge and so on. But with the coming of SWOT data, we have to think in the 2D validation, or validation in 2D. So in that case, using tide gauge maybe will not be the best solution, because unless you have a network of tide gauges big enough to make the comparison against altimeter data, it could be good. So I think that we should think a little bit about how to validate the SWOT data, and in that case, in my view, the use of HF radars and the validation of geostrophic or total surface current should be taken into account in order to validate the swap data.
Yeah, I think I definitely agree with bringing in other sensors to see what is there. And what we've actually done is that we've actually used hydrodynamic models. It's not perfect, but at least it gives you a guide, a base to go on, and then you can check and see afterwards into it. The thing is that when you're using currents, you have to be sure what they're actually calculating, which layer is, it's actually calculating the current, which layer is the satellite giving you. Is it 1 meter? Is it the surface? Is it the skim? Is it the whole part? Exactly what is it? And so these other, when you can definitely bring in other data to validate, but you need to know what it's actually measuring. What's it actually measuring?
And another problem with the HF radars that they are not located uniformly all around the world.
Yes, exactly. So it's not going to be easy. But you can also get, I think I saw, you can even get currents from the salinity and temperature. You can calculate it. There's some research being done on that too. So it's so yeah. But I think definitely you have to bring in the others. You can't expect satellite to do it alone. You have other sources there, and just use them basically. And okay.
I would like to add something about the current meters. That is something also more like oceanographic question, because with the current meters you can, or the IDCP, you are measuring the absolute velocity. So for an oceanographer or it's really interesting to understand which is the behavior of that current. For example, if you are measuring the velocity in all the water column, you can, with statistic methodology, you can separate or know which is the percentage due to barotropic component or baroclinic component. And from that, you can say, okay, I can use altimetry data to represent my currents in the area. So it's a good exercise, not only for validation, it's also for physics analysis. And you can know also that if SWOT or any altimeter product is good for your region, or you need also a model that you have the entire velocity of a DCP.
Yeah, current meter is a good source of definitely of validation for the SWOT. Shall we move on? Okay. We have the other questions.
I have a comment. I have a comment on in situ measurement. I see that many of you need in situ measurement for validation or for combination with other measurement. As you know, there is a lot of in situ measurements that are delivered by the Copernicus Marine Service. I don't know if you use this measurement, no? So I think it's important to make requirement to the Copernicus Marine Service to have the in situ measurements that are useful for you within this service, and also have processings of these measurements that is useful for you, or are less a minimum of information about different processes that can be applied on this measurement.
I said no, but maybe because we are normally using data from Puertos del Estado here in Spain, so maybe these data are in the Copernicus. So I didn't check
if they are.
But I'm using data from Puertos del Estado.
So we have other questions. I don't know. Do you want to ask a specific question?
Okay, yeah, we had the what are the existing product limitations and how to fill the gap with the needs or applications. So we had in physical variables available in terms of sea surface height, significant wave height, wind. What do users actually want? And there's a spatial resolution difference also, and what is actually needed, and how can we actually do it? And is it really needed by the community, or it's just a few people that need it? there was signal to noise ratio with the data. We talked about the coastal currents, observability, yeah, we covered that. Extreme events, any comments about it? Nobody? They come very few, but they're very important. Nothing. Okay, the nearshore and offshore product continuity in that do we want one product that goes from the coast to the offshore or separate products? I think both is useful depending on what the application is, basically. But it's always better to have one continuous product, and then if you don't want part of it, then you can just cut it off, basically. Than to have two shifts if you want nearshore and offshore. It's not going to connect in the end. But I don't know what others think about that still. It's still an important issue.
So it's the same question that was asked by the session 1 on Tuesdays. And so if I can give my opinion for the continuity between the coast and offshore product, I think it's very important to have a continuity of the signal between the two areas. Maybe not different processing, but that ensures the continuity of the different variables like sea level, significant wave event, and so on. Because this continuity in the product is very hard to manage when we are using the data for different applications. So myself, I have no application that only focus to the coast or only focus to the offshore area. It's always mixed. So we need a continuity of the product.
Yes, absolutely, Isabel. But if I may say, it's a dual problem. So it's a problem for the processing, because obviously you want to produce things that are consistent to each other, but then eventually it will also be a problem in terms of validation. So we need to make sure, like you were saying earlier, that the campaigns, the measurements are there to validate this continuity, to check that things, are consistent offshore. When from offshore you go inshore, or vice versa. So there's a validation effort that needs to be done there.
Yes.
I think that we need some study cases where we could try to put together observation and what exists from altimetry, multimission, and the model. So don't you think that it would be useful to do that? So is there an example where this work is already done?
What do you mean? Because we have models that assimilate all the measurement variables, so it's kind of a merging of all the informations.
Yeah. Perhaps it would be useful to point more on that for the other. So to present this case as the first presentation was very useful to show what we can do. Yeah.
So you mean we should ask to modelers to give their feedback about the consistency between the different products?
Perhaps, from the other side. Yeah.
That's right.
For example, also this activity that comes now with the validation of SWOT, where they have these points of crossover and so on.
Yeah.
So I am part of one, but perhaps we have to collaborate a little bit also more with the other. So I don't know if everybody knows, so there are some regions where there were campaign where we need to find that there is a model, and we will see. My intention is to work also with multi-mission at the time, because the data are there. So in these study cases, perhaps we can, from our side, try to understand what the other are already doing. Yeah? So it's, you know.
Any other comments on that one? No. So we can discuss about the next questions. So what are the criteria that tell us that a product is mature to ask for an operational production of this product? It is necessary for all the products or not? So what can we ask to different space agencies as users if we want a product? And for people from space agencies, what are the arguments that you expect from us to found some production or activities? No comment on that? Okay.
I'll start from a simple answer, I think. You need a processor in place that keeps pace with the sensing of the products and churns out level 2 products with an uncertainty. So you can even start with a product. In my view, it's open for debate. Please correct me if I'm wrong. But in my view, you can even start with a new product which is, very uncertain, provided that you've got a number for it, and people can start to see whether then, some application they can use it, and with that associated uncertainty, it's useful or not. And then with time, it will be improved because you improve the algorithms.
So you need a number of users on the product?
Well,
and maybe good feedbacks?
And good feedback, yes, okay. That's true. But like I said, I would say that defining quality for a good operational product is the characterization of uncertainty.
Okay. Maybe we can see as the next question. So how can we improve the timeliness, completeness, and accuracy of the coastal altimetry product for operational service delivery and societal applications? So it's more or less the same question to have an operational production. Yeah. Yeah. No other comment on that? So then next question. Once we say, okay, this product is mature, we can have operational production, or do we ensure this transfer to operations? Because maybe some R&D algorithms or treatment can be given to the people that will ensure the operations. Which are these people? Or do we also make the link with the Copernicus services that are operational services? What do you think about that? Okay, the same as it's the same.
I promise this is my last comment before coffee. I like to comment on this because it is relevant to Crystal that will be presented this afternoon, which is a Copernicus expansion mission. And the way that you transfer to operational production, even for the coastal area, is to have the entities that are entrusted to generate the products for the Copernicus service is deeply involved in the R&D that brings to the development of the products. And I'm speaking here for our humans, the friends you will see in my presentation this afternoon, that for Crystal, they are already planning Crystal Marine Data Center with coastal products, and there will be preparatory activities so that we make sure that we have the algorithms in place to generate these new products, and they will be part of the operational products. So better communication, yes, a link with Copernicus services, and most importantly, having the people who then are responsible for generating those products involved in the R&D from the very start, for the R&D for that particular coastal product.
So the Copernicus services, we also have high-level production that use maybe level 2 or level 2P or level 3 product from the different space agencies. And here again is maybe another processing to transfer the R&D to the operational services for this higher level production. So I think it's important from user and different laboratory to make requirements to the Copernicus services and propose also different products that they have as R&D that deserve to be put in operational production. So it's important from you and for users to make requirements, clear requirements, and propose things to these space agencies and operational services.
Maybe an end user product with a TXT file with latitude, longitude, and sea level. That's it.
Okay.
But then you have different geodetic coordinates for different areas, and that some users still might not be happy how to transfer that to it. So it might be an endless task to get everybody happy. But you need to figure out who is the majority that is using the data and what they want really, and try to please them.
From a scientific point of view, I'm quite happy using NetCDF files with 3 different tidal models, 2 different or 3 different wet tropospheric corrections, etc. And I can build my sea level anomaly or absolute dynamic topography time series. I'm happy with that. But for end users, really end users, you cannot put 3 different tidal models. You have to put the best product and with the better format or the best format for end users.
But I just had an idea. Maybe they have to go through like a questionnaire first. What area you're working in? What do you want? What do you want it for? And then you suggest some products. And then if that's not good for them, then they go to a next way, and it just calculates it for them, whatever they want in the end, converts it for the user. Not just one product, but because there's different users in the end for different reasons. So it's maybe they have to go through like a questionnaire, and then you suggest the products for them.
Yeah, I sort of agree with your last thing. Not everybody's use is the same, and particularly also with tidal models. You have tidal models that have a higher resolution but are not as accurate, and you have with lower resolution that are more accurate or missing a bit of coast here. So, but having more data there, none of that is optimal. And that's also why we have so many of those retrackers discussions of yesterday. And to say, well, this is what you get. There are, of course, products that are there, but that maybe coastal altimetry is not yet at that maturity like the ocean level 2P products, for example, that are provided by Siemens. They are actually provided by Humansat, but for Siemens, I should say more accurately. And those ocean level 2 products have sea level. Exactly what Jerome also was saying, that low sea level. That has a bit more, but that's basically where it comes down to. Maybe coastal altimetry is not there yet. There are too many usages that put some of the guys this, some of the guys that, and what if somebody has their own tidal model that they know is more accurate than the global one? They won't have it. So I think R&D products are existing and they are there for a purpose. And maybe have 5 tidal models. That's where we're at yet. I think at this point.
even at the 13th Coast Altimetry Workshop. Yeah, I think there's a few interesting points. Jesus, I think, mentioned the co-design, involve the people who will eventually use the data from the beginning. And this is what this workshop is about, trying to attract people who come here for the first time and discover, like John Wilkins said yesterday, coastal oceanographers, physical oceanographers, they don't know about coastal altimetry. They know about altimetry, but they don't know about coastal altimetry. So when we launch a contract at ESA, a research activity, the first thing, task one, user requirement consolidation. You've got a little bit in the statement of work, then you work on that, and then identifying the stakeholders or whatever, the users. And at some point, if you can identify them, or even if in the statement of work it says, yeah, you must come up with letters of support from stakeholders, because we're going to develop a product, but not just for a product, but for stakeholders. And this is very important. I think we should underline that everything we do should be done in mind with who is the user, and not develop something and then find the user, like the private sector, We develop iPhone 16 and then we wonder who's going to buy it. And so this is something that we can really write down in bold and involve stakeholders and see if there's other people than scientists who are trying to understand ocean dynamics in the coastal zone and so on. And the other thing I would repeat and repeat and repeat is to involve people who are bringing fresh water to the coastal zone. So the hydrologist, and I hope a few of you, many, as much as possible, will be interested in the hydrospace workshop, which is the equivalent on the other side of the boundary of the shore of this coastal altimetry workshop. And yeah, one last thing is that the idea is that it may be not up to this group to design these, like I said, with River and Lake, you had RLH for hydrologists and time lat long height. It may be the services, or it may be the operational arm of space, providing the services for them to find the stakeholders. Maybe the surfers or people who want to choose their beach, depending on the currents and so on, and receiving data on their iPhone. So it's important to identify the stakeholders. And we let's say, scientists developing processing algorithms, developing models of the ocean circulation in the coastal zone. We probably don't need to worry too much about, the people who are going to use the data. The millions of people who live near the coastal zone might be interested in what happens in terms of ocean dynamics or extreme events. In fact, this is also very interesting. But more the physical oceanographers that use in situ data and that's it, and don't know about activity. These people, we should try to find them. Like, this is the comment of John Wilkins. And my final comment is that I was told that the coffee is hot and ready anytime you want.
I just have one more comment. I used to work in industry before, and I think the engineers are very much interested in what's going on. They just don't know how to do it. And as you said, it's about making them aware and feeling comfortable. They go check out the site and they get afraid of it, of using the data. So it's about feeling comfortable too, to use the data and confident about it.
So perhaps I add a couple of points. So about that, coastal altimetry products. So first we need to be ask ourselves, we want to deliver our products really targeted at the scientific community, or at the end users. So like as myself is just a scientific user, so I would like to see coastal altimetry products to have more options. You have different models included and different variables, so I can do my own manipulation and to try to understand, the user-based data and to get best science. And then I can serve the end communities. So for example, coastal communities and engineering firms, by that time I will develop products to be very simple for them to use. But with our community here, we are talking about we need to deliver that simple product. I think really we need to ask ourselves what's our main objective and goal or our mandate. And I think it would be very difficult in terms of the complexity of the coastal altimetry product and also the accuracy of the product if we try to simplify things and just to directly meet the end user. I think at this stage it will be quite a challenge. So I would prefer to see, we develop product that has tried to improve the accuracy for the communities so we can derive best information and to serve the end users.